Welcome to Unit 5 on sampling distributions for AP Statistics. In this video, we're going to focus on topic 5.8, sampling distributions for differences in sample means. All right, why would we possibly want to compare two samples from two different populations? Well, one thing many research studies aim to do is to see if there is a difference between two different population means. For example, a teacher might wonder, hey, what's the difference between the mean amount of time per week freshmen spend on homework and the mean amount of time per week seniors spend on homework? An economist might wonder what is the difference between the mean salary of females and males in the business industry. And a doctor might wonder what is the difference between the mean blood pressure of African American men and white American men. So oftentimes researchers aim to look at the difference between two populations. Now we are measuring the same thing from those two different populations, right? We're never going to look at a problem where we're looking at the mean shoe size of men versus the mean salary of women. I mean, that would be a stupid thing to compare. So we are going to look at two different populations. For example, men versus women, seniors versus freshmen, white American men versus African American men. But regardless, we're going to measure the same thing, whether it be blood pressure, salary, or how much time you spend on homework per week. Now, it's important to understand that if we're going to answer any of these questions, we have to take a look at samples, right? We can't ask every single person out there how much time they spend on homework or what their blood pressure is or what their mean salary is, but we do have time to get to a sample. But recall, that's kind of been the theme of this whole unit, is that just looking at one difference between two samples doesn't really tell us a whole lot. What we need to do is consider what all possible differences between two samples would be. So if I got two samples, one of men, one of women, and I looked at the salary for the men, I looked at the salary of the women, I'm going to get a difference. But if you went and did your own research, you got your own sample of men, got your own sample of females, and looked at the difference, you're going to get something different from me because that's what samples do, is they vary. So what we want to do is we want to get a feel for what do all possible differences out there look like. And this, of course, would be a sampling distribution. Now, again, a picture of all possible differences between two samples from two different populations is a sampling distributions, as long as we're keeping the sample size consistent. So if I look at 40 men, you need to look at 40 men. If I look at 35 women, you need to look at 35 women. All right, we need to have the sample sizes be consistent there. All right, so we need to build a sampling distribution. Let's just get down to it, right? We've been doing that all units. We know exactly what this is about. But we need the focus here is on the difference between two sample means taken from two different populations. And what's crazy is by the end of this video, I've said this 4 times now, we're going to be able to understand what this sampling distribution looks like without even taking a look at any samples. All right, now it's important to know that we are looking at two different populations, so we do have a lot of symbols going on here. First, we have population 1. Now, generically speaking, I'm going to leave this in terms of 1s and 2s, but in a real problem, feel free to actually use some abbreviations here for your problem. But keeping it generic, population 1 will have a mean and a standard deviation. Those values are going to be needed. I need to know what the population is doing. And population 2 is also going to have a mean and a standard deviation. And I need these subscripts to kind of differentiate between the two of them. Now, I also need to understand that a sample from population 1 is going to be different than another sample from population 1, right? Because there is only one true population mean, but there are many, many, many possible sample means. And that could be said as well for population 2. And then we also need to keep our sample size the same. Now, this is important. The sample size from population 1 and sample size from population 2, those could be different, right? I could look at 40 males and 35 females, but what I mean to say is that we have to be consistent for our sampling distribution. So every difference in our sampling distribution is going to be for a sample of 40 men versus 35 women. That cannot change, but the sample sizes in the two different populations can be different. Now, let me give you an example of what I mean by the 1s and 2s are very generic. If you're going to do an actual problem, you need to be much more specific. So let's just say we are looking at our freshmen time they spend on homework versus our seniors in time they spend on homework. So maybe in an educational journal, I read that the true average amount of time a freshman spends on homework is 250 minutes per week with a standard deviation for the freshman of 43 minutes. So notice the abbreviations I'm using. In the past, we just used mu and sigma, but that's because our problem was only looking at one population. Well, now we're looking at two, so we need to kind of denote the differences between them. So the mean for seniors, again, maybe I read this in Education Journal, they only spend 175 minutes per week on homework. and the standard deviation for seniors is 30 minutes per week on homework. Now, let's just say I look at a sample of 37 freshmen and a sample of 42 seniors. Again, now what I'm doing is I'm building a sampling distribution. I'm saying, hey, a sample of freshmen, oh boy, it doesn't have to be 250. It could be anything, right? A sample of seniors, man, it doesn't have to be 175. It could be anything, right? I'm talking about a sample. And I understand that samples vary, right? But what we're looking at is the difference between these two samples. So we want to build a sampling distribution showing all possible differences between a sample of 37 freshmen and 42 seniors. Now, to do that, we need three things. The first thing we need is the center, right? The center is literally the mean of all the different possible differences. Like I said earlier, I could get a difference between two samples. You could get a difference between two samples. Sally could get a difference between two samples. We're all going to have different differences. And the idea is that if I take a mean of all those possible differences, I should get the true mean. So again, notice the symbol here, the mean of all possible differences. Now for my specific problem, the mean for the freshmen was 250. The mean for the seniors is 175. That is a 75-minute difference in favor of freshmen. So that means I would expect any two samples, one of freshmen, one of seniors, I would expect that sample to have a difference of 75 minutes, but I also know it's going to vary. That's just the mean of all potential samples. Now, of course, there's a condition here. Both samples have to be random to avoid being biased. If there's any bias going on, you're certainly not going to get the truth. So if the truth is 75 and you are consistently not getting 75, like listen, I understand some samples could be 76, 77, 74, 73. I get it. Totally makes sense. But if you are consistently getting differences to be 45, 45, 45, 42, 42, then you're probably going to have some bias. All right. The spread, right? We understand that my difference might be different than your difference, might be different than Sally's difference. So there's going to be a standard deviation of these differences. So once again, note the differences here, or notice the symbols here, the standard deviation for the difference between two samples. Now, pretty easy formula to follow, but a lot of kids say, well, where's this formula from? I will walk you through that in one moment. But the formula is to take the standard deviation from the first population squared, divided by the sample size from that population, plus the standard deviation squared of the second population divided by the sample size taken from that second population. Now, of course, for this formula to work, we need the samples to all be independent of each other, which goes back to that 10% condition. It doesn't make sense to us to always sample with replacement. Oftentimes we do not replace, but as long as our sample sizes are both under 10% of our populations, any differences that might exist between the samples is going to be a negligible one. All right. Let me show you real quick how this formula works, okay? So if I'm actually going to use this formula for my freshman versus senior problem, I'm going to look at, okay, the freshman had a standard deviation 43. That needs to get squared. Divided by my sample size of freshmen was 37. Plus the standard deviation for the seniors was 30 squared. Divided by the sample size of seniors was 42. And I need a giant square root around all of that. When you type this into your calculator, if you're using a TI-84, you really do not need any parentheses at all. Just start with the giant square root and just start typing. And you should get 8.4499 minutes. Now, I want to make sure everybody is crystal clear on where this new formula comes from. So let me talk about that very briefly. All right. So the standard deviation of a single sampling distribution, looking at just one mean for one population, we learned in the last topic, is the standard deviation from that population divided by the square root of its sample size. But if I have two of these, one for population 1 and one for population 2, well then I essentially have the same formula twice. I am going to use some 1s here and some 2s here to denote the two different populations. But again, I need to combine these two standard deviations, but I got to follow two really important rules. First, I'm not allowed to add standard deviations. I have to only add variance. So how do you find variance? Guys, it's as simple as taking your standard deviation and squaring it, which means this entire value needs to get squared so that it turns into variance. Same thing here. The moment you take a standard deviation squared, now you have variance. Now check out what happens when you square these numbers. The number on top, which is the standard deviation from population 1, does get squared. But on the bottom, when that square hits the square root, the square root cancels out. So I did square both the top and the bottom, but in the bottom, it gets canceled out with the square root. Then I'm going to do the same thing for the second population, standard deviation. It's going to get squared. But again, on the bottom, the sample size will just turn into n. The square root goes away. So I am following the rules of algebra. I'm squaring both the top and the bottom, the numerator and the denominator. But in the denominator, the square root cancels out with that square. Now, the second rule I have to follow is that I only add variance. Even though this whole topic is looking at the difference between two samples, variance always builds. So once I have all this variance put together, now I have a giant square root around all of that to get my standard deviation. So that is why the standard deviation for the difference between two sample means is this formula. So please make sure, I will kind of go through, there's actually 3 common mistakes, but the top 2 common mistakes are kids don't square the standard deviations on top because they're used to the original formula for a single population where it doesn't get squared. Well, sorry, new formula. The second thing kids do quite frequently is they mix up their sample sizes. So if we go back to the formula that I did for our freshmen versus seniors, a lot of kids will be moving too fast and they'll put the 42 seniors under the standard deviation for freshmen, and they'll put the 37 freshmen under the standard deviation for seniors. The third mistake that some kids do, this is a rare mistake, but I like to point it out because a lot of kids will make it every now and then, is instead of using the standard deviation, they'll accidentally use the means of the population. My goodness, don't ever do that. That's a really big issue. That's obviously going to get you the wrong answer. So make sure you're really organizing your work and using the standard deviation. All right. So we already talked about, but I just want to bring this slide up again. This is actually the 4th time you've seen a slide similar to this. And it's really important that you do understand this, right? We need the sample sizes to both be under 10% of the populations they were selected from. The reason for this is because we need all of our samples to be independent of each other, which if we're not replacing our samples, we're actually not going to have independence, because every time we take some people from the population and we leave them out, well, technically the population's changed. But as long as our sample sizes are under 10% of the population, any change to that population is what we call negligible, meaning it's not a very big difference for us to worry about. All right, the other big important thing I need you to understand, again, for the 4th time in this topic or in this unit, is that bigger samples vary less. Bigger samples vary less. Bigger samples vary less. In all formulas for the standard deviation of a sampling distribution, the sample size n is in the denominator. So when our sample sizes get bigger, our standard deviation shrinks. So if you think about a sample of 100 seniors, that sample on average is going to vary far less from the truth than a sample of, say, 5 seniors. So it's important to understand that bigger samples do vary less. All right, the third aspect to any sampling distribution is, of course, the shape. And we really, really need that shape to be normal. That way we can utilize the normal model to calculate probabilities. So how do we know that the sampling distribution for a difference is going to be normal? Well, it goes based on 2 things. One is that if the populations are unknown or non-normal, then we do need the central limit theorem. Remember, the central limit theorem tells us that the sampling distribution for sample means is going to be normal as long as you are sufficiently big enough, which we say is 30 or more. But don't forget the other aspect that we've explained to you, is that if a population is already known to be normal, then all of a sudden we don't need the central limit theorem and any sample size is big enough. So I think it's really important that you hear that, right? If populations are already normal, then even a sample size of 1 seems pretty small. Yeah, a sample size of 1 is definitely going to vary a whole lot, but a sample size of 1 is going to produce a normal model because the population is already normal. So truthfully, the central limit theorem is really only needed when the populations are unknown or specifically given to you as non-normal, or maybe skewed left or skewed right. If that happens, we do need our sampling distribution, or our sample size, to be 30 or larger so that the sampling distribution can still be normal. All right, so here's kind of a summary of everything we just went over, the 3 big important parts to a sampling distribution for the difference between 2 sample means. First, the center, the mean of all possible differences is going to be the true mean between the 2 different populations. The standard deviation that allows them to deviate is as follows. We talked a lot about that formula, and the shape is going to be normal. But please do not forget the conditions. Anytime you're asked to describe a sampling distribution, you need all 3 of these parts and you need the conditions that allow them to be true. And the funny thing is this, even if you were given a question where you were asked to calculate a probability, you actually, think about what you need to calculate that probability, right? First, you need it to be a normal model. That way we could use our calculators and use normal CDF. So we have to make sure that third condition is checked. Then we can't use normal CDF on our calculator unless we have a z-score. Okay, but to get a z-score, we need to know the mean. We need to know the standard deviation of that model. So I can't technically calculate that probability until I check all three of these things. That's why these three things are so important when it comes to creating a sampling distribution. All right, now we can build a sampling distribution without even taking a single sample. It's really crazy, but all we need to know is the true population mean and standard deviation from each population. All right, the last thing I'm going to leave you with is oftentimes when we're comparing two different populations, when we're comparing two different samples, we want to ask you about when is one possibly going to be bigger than the other. And this is where the order you subtract does matter. If I'm looking at the mean of a sample from population 1 versus the mean of a sample from population 2. Now, this is where it's super important to understand that 0 is where they're going to be tied, right? So if I want the sample from population 2 to be bigger, that means I'm looking for a value less than 0. Because if this second sample from population 2 is bigger, and I'm doing it in the order of 1 minus 2, then that means I'm going to get a negative difference. Because if the second guy is bigger, when you perform subtraction, you are going to get a negative number. So that's why 0 is a really important number, right? Because if you have a difference of 0, it means your two samples are tied. They're both the same. But if the difference is positive, that means the first sample is going to be bigger. And if your sample difference is negative, that means the second sample is the one that's bigger. So it's important to understand when you're comparing and just saying, hey, which one is bigger, that's when you really got to focus in on 0, okay? So I do want you to better understand all of this through an example. So there is going to be a follow-up video that does explain an example using all of this information. That way you can really kind of put all the different pieces together and see how it works to actually calculate a probability. So stay tuned to that video and we'll see you. And this is the last topic from this unit. So hopefully everything is starting to kind of come together and make a lot of sense.